This is Mr. Anderson for Kellogg Community College. Today we're going to talk about common logs and natural logs. This is section 5 of chapter 9 in Math 121 Intermediate Algebra. We're going to do a couple things. In an earlier section, I told you that if you had written down log base 10 of x, that isn't actually simplified correct, and that's because common log is base 10. Therefore, writing common log is just the log without the base written. So, like 1 times x, we don't write that, we usually write x. We will not write log base 10 because common log is just log of x, which is the same thing as writing 10 to the y power is equal to x in this situation. The natural log, again, we had a problem earlier on where I had log base e written for you, and I said log base e isn't actually written that way. It's written as natural log, and natural log of x is the same thing as log base e of x, because natural log is log with a base e, and e is approximately 2.718. And it goes on forever. It is a non-terminating decimal, and there are great videos and lots of proofs. In this fact, there's a little demonstration of it in the book, and there's really neat things to figure out e. But please search those out yourself. So when you have the natural log of y, it's like saying log base e of y, which is the same thing as x. So e to the power of x is equal to y is an equivalent statement to the natural log of y. Now what you're going to do next for the problem, in problems 1 through 6, is you're going to type these into the calculator and get your answers. And we're going to round those to 4 decimals. Now on your calculator you have these tools available to you. So for example, log of 7, what you have here is you're going to click log 7, and round this to the 4th decimal would be 8,451 10,000ths. You're going to always please round correctly, which means that you look at the 5th decimal, and if it's 5 or above, give it a shove. 4 and below, let the 4th one go. Now for problem number 2, if you type in the log of 25 hundredths, you will get negative 6,021 10,000ths. And problem number 3, log of 5,700 divided by, now make sure you put your parenthesis in there, divided by log of 5, because these are both base 10 problems, will give you 5 and 3,734 10,000ths. When you get to 4, 5, and 6, you can use the natural log, which is underneath the log key, and that you can type in just as so. The applications will be coming up later on. We'll be doing some story problems with these, and this is going to be 2 and 5,694 10,000ths. And number 5, we'll have the natural log of 1900 divided by 0.07. Notice that is not a log, it's just dividing by 7 hundredths, and this gives us 107 and 8,516, rounded up, 10,000ths. Problem number 6 is going to be e raised to the 2.71 power. Now this e is also available right there. If you click second natural log, you get the e there, and it's always a power. So e raised to the 2 and 71 hundredths power is going to be 15 and 293 10,000ths. So without going back to the pen and writing all these in, these are quick answers you can get on the calculator. Now, earlier on, I had a problem for you because the problem asked like 3 to the x is equal to 50. And we couldn't figure that out. We couldn't figure that out because we did not know what power of 3 would give me exactly 50. And where I was stuck, and this is back in section 3 here, where I was stuck is we try to go 3 to the, maybe the 3 to the 3rd power, which was 27, and then 3 to the 4th power, which was 81. So 3 to the 3 point something power has to be 50. So what we're going to do is use something called the change of base formula. And the change of base formula works like this. If I have log base b and I'm trying to find my answer of y, then we're just going to take the log of my answer y and divide it by the log of my answer, or my base b. Now in the book they have little subscripts here for the log property that you can use. You can use any log base that you want, but since the calculator works in base 10, we're going to use log of y divided by log of b to figure out what my number is. Which means that if I'm trying to find this problem, I'm going to convert this to log base 3 of 50 equals x. Which means that I'm trying to find what's the power of x, what's the power of 3, so 3 to the what power is 50. So using my change of base formula right here, all I have to do is take my log of 50 and divide it by the log of 3. And when you do that division, you would get your answer for x. And in this case, if you type this in on the calculator, making sure that you put the parentheses in after the log of 50, this gives you 3.5609, rounded to the fourth decimal, or 5,609 10,000ths. So problems 7, 8, 9, 10 really become a situation where we're going to take these problems and just do the change of base formula. Now what I'm writing down while I'm speaking here is how you would do that. Your answer divided by the base will give you the exponent. So if I raise 2 or 7 to the 2.3666, or 2 and 3,666 10,000ths, I will get to 100. So this is what I'm finding. And that was impossible until I got my change of base formula. And this also, a quarter raised to the negative 2 and 3,219 10,000ths power gives me 25. So a quarter raised to the negative 2 and 3,219ths power gives me 25. Which is neat because the negative exponent turns that from a 1/4 into a 4, and then 4 to the 2.3219 power gives me 25. Now this one's kind of funny because if you do your log of change of base formula, you log of 500 divided by log of 10, you get an answer that's approximately 2.699. Even though it says round to 4 decimal places, this 89 would have been rounded up to 9D. So 669 thousandths, or 6,990, 6,990 over 10 thousandths. This problem right here is kind of funny because log base 10 of 10, this is 1. So in fact, this really is log of 500, just to give us this right here. And for our final problem here, this is another kind of interesting problem because this is just log of 10 divided by log of pi. This is another problem that's, technically 1 in the numerator here because log base 10 of 10 is 1. So this, when you do the change of base formula, it gives you an approximate answer of 2 and 115 10,000ths. Now what I've left off here is I've left off the proof. There's a proof to the problem because some of you were thinking back a couple sections ago, well, if I'm going to solve for x, let me just divide both sides by b. But that you can't do. So what I'm going to do is do the inverse property of exponentials, which is log. So I'm going to take the log of both sides, which is a legal step here, and we'll see more of that in section 6. And this is going to be log base b x, and this is log base 10 b to the x and log base 10 y. Now, because of our power rule, we can take the x and move it out in front and change it into a product. So this is our common log b, and this is our common log y, and then we move the b to the other side to get x by itself. So now we have common log y, and we have common log b. Now compare that versus this equation, and you'll see they're exactly the same things. So that the proof is pretty easy. The book might use little subscripts to denote that you don't have to use base 10. You can use any base, but I used base 10 just because that's what you have on your calculator. Well, thanks for watching the first part of this worksheet. On the second part, we're going to deal with the graphs of E and their inverses, the natural logs.